Hello guys, welcome back to Random Access Projects. Today I have a ball and beam setup here for you, and this is a typical control system engineering problem that I've solved with this setup that I want to show you in a little while. But generally speaking, this is a control system that is programmed into our brushless motor driving board. This is the brushless motor, and the brushless motor acts on a beam which has a ball on top. That's why it's called the ball and beam problem. And the idea is that the motor must rotate to make the beam go up or down in order to make a ball slide on top of it to different locations along the beam. And the idea is that a sensor, which in this case is located here and is an infrared sensor, can measure the distance to the ball, and using that as feedback, the control system will be able to drive the ball to a specific point along the beam. This system will tend to oscillate, as we can see it's doing right now. This kind of systems tend to oscillate, and we'll see why is that. But the idea, once we have succeeded setting up the system and tuning the parameters for the proper control law, it should behave something like this. It should be very close to this position. As you can see now, it's almost stopping there, and now it has stopped. So the idea is that it will get to this point by itself. Right now, if I push the ball away, it's not getting back to that position. But with some good code and understanding of what's going on in this system, we're going to be able to make this happen. So come with me and I'll show you how I made this. Let's begin by taking a look at the system. I first modeled it using Fusion 360, and you can see the brushless motor over here, and I did a bit of a animation with the joint, so you can see that when the motor rotates, it actually drives the beam up and down from one of the ends, causing it to change the angle. So here it is again. We just see how the ball is supposed to move along. This is a very crude animation of what must happen, but it gives you an idea. And now let's look at the setup in real life. So you can see it here. The base, this black thing, is made out of Valchromat, which is a high density or HDF. And let's zoom in a little bit, and then we can see how our connections are made. So here we have the 12 volt plug coming into this board. This board, we're just going to use the breadboard for taking 12 volts into the new version of the board that we have presented in previous videos. Now, this new version of the board has output for 2 brushless motors, and our brushless motor is connected to one of them. At the same time, we have the encoder coming from the brushless motor connected into one of the ports. The other port is where we have the infrared sensor connected to. So this infrared sensor is going to measure the distance that, it's going to measure the distance between the sensor and the ball. We have this stops here, so we don't allow the ball to get too close to the sensor. We're going to see why. The sensor is non-linear, so then we approach a non-linear region there. So we have to keep it within these 2 stops. And that's pretty much it. We can see the link needed and how it affects the behavior of the system. So there it is. This is a very good resource for control tutorials, and it's made by University of Michigan originally. What we want to do is find this ball and beam over here, press on it, and the first thing we're going to see is the introduction to it. So the physical setup is right here, and basically is what we have done. We have a beam, we have a ball on top of it, the beam has a certain length, and there is a distance between the end of the beam and the ball, and that R is what we want to control. And to do that, we're going to affect the angle alpha, which is going to lead the ball to go either way. And that's going to be done by means of this lever arm, which is being pushed by this motor. So an angle theta here will cause an angle alpha, and this is a nonlinear relationship, but I guess some simplifications will be made. So this is the physical setup, and then we have the bunch of parameters, radiuses, etc. And this is to get an analytical approach into solving this problem. It's amazing how once we apply the Laplace transform, then we get our transfer function, which is telling us that our system is a double integrator. And it is marked here. It will provide a challenging control problem. So that's why this is one of my favorites, because it's not that easy to solve. It's a little bit challenging. So let's jump right into this. I'm going to explain you why this is challenging. Let's look directly at the ball and beam without any feedback. This is the open loop, and you can see how the program is foreseeing that the ball will just run out of the beam. So we're going to program 0 and 0 in the controller, and then as I push the ball, you can see how it just follows till the end of the beam. Now let's close that loop. Let's put some feedback. So we have the ball and beam, and we have our control, and then as you can see now we have a set point and also a position of the ball that is being sensed using the infrared sensor. So by taking the difference between these two and inputting that into the control, that's how we get to control the position of the ball. Now I'm going to explain what this blue box here means. It actually means that inside the ball and beam system we have a subsystem, which is our servo motor or our brushless motor in closed loop. It has a proportional control and it has some feedback given by the encoder, but the flow is the same. It's just part of it. Now let's look at how proportional control would work, and in this case we have marked here our box for proportional control, and this is what the simulations, the MATLAB simulations are suggesting the behavior of the system is going to be with a proportional control. So let's program our ball and beam. Let's just modify the KP for this is the gain for the proportional part. Let's put it into 1, and let's start our demonstration from the same spot. We can see that there is a lot of oscillations, but if you look close to the left stop, you will see how the ball goes to a different point every time. So you can see as we fast forward that it is actually being attenuated. It took a good 30 seconds to get to this point, so we're going to try to improve this by adding a larger KP. So now we have a KP of 2. What some of us would expect would be to see the ball converge faster and arrive at that stability point faster, because now we have a higher gain, right? But not in this kind of system. In this kind of system, it continues oscillating. Let's try 3 for the gain now. And as we can see, the oscillations are still there. They're even amplifying to the point that the ball is crashing with a stop every time. So just for fun, let's check what a K of 4 will do. Let's take the gain up to 4. So with all these observations, we could start concluding that there must be something in the nature of this system, some underlying aspect of it that prevents it from being stable with a proportional controller. So by adding the derivative term, we will be able to change the behavior of the system. So we have it here, it's just the PD control. We still have a proportional control inside the loop for our brushless motor. We just modified the outer loop, so to say. And what the analytical study tells us here is that our system is going to stabilize at the 25 centimeter mark that we gave it. It's going to have some overshoot, but it should become stable by adding this derivative term. So now let's go to a Kp of 2 and let's put a Kd, which is the gain for the derivative term, of 3, and let's test it out. And right away we can see that we have succeeded in solving this problem. And to me, it's amazing how the addition of this derivative term becomes the cornerstone for solving this problem. Normally, you would use a derivative term for improving the response of a system. But in this case, you cannot have a stable system if you don't have this derivative term. So that's what I find fascinating about this problem. Let's continue tuning our controller. I'm just going to add a little bit more of the derivative term and see what the response is. And we can see that this is very good, guys. We have reached steady state within a few seconds. The problem is now solved. Let's look at the schematic, and in the middle you can see the brushless driving board with an embedded Arduino. We have the programming port, and we're supplying this board with 12 volts. To the right we see the connection to the motor coils A, B and C, as explained in previous videos, and also we see the connection coming from the motor's backpack with the encoder, and that connects into one of the ports. And on the other port we see the distance sensor, and we're going to talk a little bit more about that in a second. So this is a sensor we're going to be using. It's made by Sharp. It has this weird number. It's quite compact and easy to connect. And this is an important chart. It shows the nonlinear behavior of the output for this sensor. So you can see there's a linear behavior going from 0 to around 6 centimeters. And then there's a nonlinear behavior starting around 7 centimeters and going all the way to 80 centimeters. The most sensitivity is in the first part, between 10 centimeters and 30. So that's why I like to use a sensor, because that gives you the widest range of voltage. But we're going to have to linearize this sensor, and I'm going to show you how we're going to do that now. So one of the ways of doing this is to make a chart, and you want to put the different distances on one of the columns. You're going to put the ball in these distances, and then you're going to measure what the output of the sensor reads like in the Arduino. So that's just the analog to digital converter value. And then you're going to get a chart like this, and here you can see the nonlinearity. Now you want to make sure that the values from the analog to digital conversion are on the x-axis, while the distance in centimeters goes into the y-axis. So that when you create the trend line, you can get an equation that is in the right order. So we're going to add the trend line, and you want the trend line to be a polynomial. So a second order polynomial kind of fits, but of course a fourth order polynomial is going to be the best fit. That's going to give you an R value of almost 1, so it's 0.99. And this is going to be a little bit hard to evaluate with the Arduino. It is possible, but you might run out of variable space. So I just go down to second order. It's not a great fit, but still 0.96 fit is kind of okay. And we're going to use that mainly in the range between 10 centimeters and 30 centimeters, maybe 35. So that should do well. And then you're going to input this equation to calculate the distance. So just the same equation that you get from the trend line on Excel is what you plug directly into the Arduino code. Now that we know how the linearization works, let's look at the flow of the code. The first part is a 5-frame averaging filter, which will help us keep the signal from the distance sensor clean. This is a low-pass filter, and it's very easy to implement and even to understand how it works. So basically we end up with an x value, which is the distance, and that is the average of the last 5 measurements that have been taken. So every time you take one new value, then the last one is discarded. And this is very fast to implement. And what we do is we take that x value and we fill in the linearizing equation in order to obtain this variable called distance. So this will give us the distance to the ball. We finished doing the calculation for our proportional differential control right here. So we have that the output u is going to be the proportional term plus the derivative term. And this is where you see the kp and the kd, which is what we are going to tune, or we already have shown how they're tuned. And this is the actual error, and this is the differential error between the previous error and the actual error. So you can see that it's calculated here. This differential error uses this error and the previous one. So that's how it's calculated. At the end, we define the set point where we want to send the motor. So now we're talking about the motor control loop, and that is going to be given by a bias, which is the value that we send to the motor so that the beam is flat. So 190 is what in my setup makes the beam flat. And to that we just add the output of the proportional derivative control. One last thing to notice is that because this is 2 control loops working one inside the other one, if I affect one of the control loops tuning, that's going to have an influence on the whole system. So right now I have changed the proportional gain from the motor. I doubled it, more than doubled it. It went from 3 to 7, and you can see how the system is much more nervous now. You can see it's a bit more violent, and that's because the K is larger. So you can see that even in steady state, noise is turned into movement. I want to show you how this whole setup looks through the eye of a thermal camera. So you can see the sensitiveness of the camera as it picks up the residual heat from my hand on the table. Now if you look to the sensor, you can see the heat generated by it. Also, if we zoom into the controller board, we can see that the MOSFETs are quite cool. It is the 5-volt regulator that is producing the most heat, but still within range, as it still below 40 degrees centigrade. And now we see the motor, which is also running quite cool. So everything is under control here, and one last time we're going to see the system work in infrared. Hey guys, this video took longer to make than I originally expected, so it's already another day and it's midnight. So I hope you enjoyed this video, and I want to leave you with one more video that I shot back in 2008 in the BMW Museum, and this is in Munich. They have taken down this installation, but hopefully you find it interesting, and just think about the setup that you saw today and think about how much more complicated the following setup is. That's it for today. See you soon.
Too geil, das ist runtergefallen.
Echt mit?